Welcome back to Differential Calculus. In this video, I want to look at evaluating limits at infinity. We've already looked at the graphical idea, the interpretation of what's happening here. And so in this video, I want to start using the formal definition. Before I get there, though, I want to remind you the definition that we say that the limit as x approaches c of f of x is equal to L if and only if for every epsilon greater than 0, there must be at least one, and in fact there must be infinitely many, delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus c is less than delta. We then saw that the limit as x approaches c of f of x might be equal to positive infinity if and only if for every capital M greater than 0, there must be a delta greater than 0, such that f of x is greater than m whenever 0 is less than the absolute value of x minus c is less than delta. And so when we looked at this case, we looked at infinity happening over here. We replaced this absolute value of f of x minus L with f of x greater than m. Using that as our template, it should make sense that if we want to talk about the limit as x approaches infinity of f of x being equal to some constant value L, we instead replace the thing happening with x, right? We replace the 0 less than x minus c less than delta with x greater than m, and we get that this limit is true if and only if for every epsilon greater than 0, there must be an m greater than 0 such that f of x is less than, or f of x minus L is less than epsilon whenever x is bigger than m. The important thing for us with this definition is that all three of these definitions follow such a similar structure. They are so closely related to each other that all of the properties of dealing with limits, when we had the finite case that's now half off the screen, should work the same or at least very similarly in the other cases. And that's the tool we're going to be using to our advantage here. If I want to evaluate the limit as x goes to infinity of some rational expression, x squared minus 5x plus 6 over x cubed minus 7. But using the properties of limits, I should be able to split this limit across the division and separately look at the limit as x goes to infinity of x squared minus 5x plus 6 and the limit as x goes to infinity of x cubed minus 7. From there, I should be able to use linearity to split this up further. And for the sake of fitting everything on the screen, I'm going to do two steps at once. I'm also going to use the power rule so that I can say that this is the limit as x approaches infinity of x squared minus 5 times the limit as x approaches infinity of x plus 6 all over the limit as x approaches infinity of x cubed minus 7. Unfortunately, when we try to evaluate this, the limit as x approaches infinity goes to infinity. And if you take infinity and you add or subtract anything, well, you still get infinity. So we end up with infinity over infinity. Which is another indeterminate form. Infinity over infinity indeterminate forms are incredibly common whenever you take a limit as x goes to infinity. Let me grab that original expression, and just like when we've had indeterminate forms in usual limits, whenever we have an indeterminate form in this sort of a limit, we're going to look for a way of making everything work out. The way to do that in this case is to find your largest power on x, which in this case is the x cubed in the denominator, and divide numerator and denominator by that power of x. So this has to be equal to the limit as x approaches infinity of 1 over x minus 5 over x squared plus 6 over x cubed all over 1 minus 7 over x cubed. Now from here, we can split that limit up the same way we saw the first time through. Although instead of getting limits on x, we're going to get limits on 1 over x. I'm not going to go through and show all the details. It is the exact same process. We're going to have the limit as x approaches infinity of 1 over x minus 5 times the limit as x approaches infinity of 1 over x squared plus 6 times the limit as x approaches infinity of 1 over x cubed. In the denominator, we're going to have 1 minus 7 times the limit as x approaches infinity of 1 over x cubed. And in the last video, we saw that the limit as x approaches infinity of 1 over x is 0. So this is 0, and this is 0, and this is 0, and that's 0. Everything goes away except for this nice factor of 1 in the denominator. The limit in this case is 0. Based on what you've seen in previous courses studying the horizontal and vertical asymptotes of rational functions, that should be expected of. One of the rules of thumb that you learn in algebra and trigonometry courses is that whenever you have a rational with a smaller degree polynomial in the numerator and a larger degree polynomial in the denominator, when you take the horizontal asymptotes, always going to be y equals 0. So we don't get any surprise here whatsoever, although it is nice to confirm that the rules we have just developed follow the same process as the rules you've learned previously. The interesting case here, much as in the previous video when we were doing things graphically, is what happens when you are looking at something involving a square root. So let me look at that next. I want to take the limit as x approaches infinity of x over the square root of x squared minus 1. If I just try plugging in x equals infinity, this is again going to take me to the infinity divided by, well, the square root of infinity squared, which is infinity, an indeterminate form. But if I try to multiply or divide by the largest power, like I did for the rational function, it gets kind of messy because of the square root. I know that x is equal to the square root of x squared if x is greater than 0. So I guess that in some sense, it is the same power in the numerator and denominator. So I can take x and divide by x, and I can take the square root of x squared minus 1 and divide by x. Which is the same thing as, all right, I'm not going to waste any more time in the numerator. I have x divided by x, which is just 1. But in the denominator, dividing by x outside of the square root is the same thing as dividing by x squared inside the square root. And now I can take my limit, right? I know that the limit as x goes to infinity of 1 over x squared is going to go to 0. That goes away. So I'm left with 1 over the square root of 1, which is just 1. Not a whole lot going on there. Where things get interesting is, what if instead of taking the limit as x goes to positive infinity, I needed to take the limit as x goes to negative infinity of x over the square root of x squared minus 1. In order to do this, I no longer have that x is the same thing as the square root of x squared. Because if I take a negative number and I square it, it becomes positive. So I have a negative value over here and a positive value over there. In the numerator, I can still just divide by x without any trouble whatsoever. In the denominator, instead of thinking about that as dividing by the square root of x squared, I have to divide by the opposite of the square root of x squared. Giving me this extra negative sign hiding in front. The 1 over x squared still goes to 0. Everything else works the same way. We get 1 over the negative of the square root of 1, which is negative 1. That's the process that you're going to see quite a bit when you are looking at trying to find horizontal asymptotes for expressions like this. The limit as x goes to positive infinity and the limit as x goes to negative infinity. Whenever you have a square root involved, you have to worry about, well, to get that x inside the square root, I have to think about whether it is positive or negative. And when it's negative, a negative sign is going to show up. That is the one place you have to be careful. So with that in mind, I'd like you to try one similar to this. I would like you to evaluate the limit as x approaches negative infinity of 3x squared plus 4 all over x plus 6. Right? Take a couple of minutes, see what you can do with that one, and I will see you in the next video.